In this video, we're going to do the first of many challenges. I tried to make these challenges align with what we've already learned, but in some cases, the solution requires a new function or trick that we haven't discussed. Now that's on purpose because in the real world, the problems you come across aren't limited to the things you've already seen. So part of being a good data scientist is having that ability to search for a solution online and to read and interpret documentation. So I'm going to encourage you to do all of those things in your attempt to solve these problems. All right, let's get started on the first challenge. You and your spouse have decided to let the internet name your next child. You've asked the great people of the web to submit their favorite names, and you've compiled their submissions into a series called Baby Names. Determine how many people voted for the following names: Chad, Ruger, and Zeltron. As they say, there's many ways to skin a cat, but here's the solution that I came up with. The key to my solution is to use the value counts method, which returns the frequency of each unique element in sorted order from most frequent to least frequent. So you can see babynames.valueCounts is a series whose index has the unique values of baby names and whose values are the corresponding frequencies. Since we want to get the frequency of Chad, Ruger, and Zeltron, we can chain babynames.valueCounts with .log, passing in a list of index values we want to select, in this case Chad, Ruger, and Zeltron. Given two series, B's and Ni's, if the ith value of B's is nan, double the ith value inside Ni's. Here's the solution I came up with. Let's break it down. pd.isn'aBs returns a Boolean series indicating whether each element of B's is nan. .toNumpy then converts that series into a NumPy array. Piping that into Ni's.log selects the elements of Ni's where corresponding array values are true. And finally, star equals 2 updates each element as 2 times itself. The tricky part of this problem is knowing how to avoid index alignment, and that you need to do it in the first place. If we didn't use the toNumpy method and left pd.isn'aBs as a series, then Ni's.log would actually select elements of Ni's whose index matches the index of true elements in the series returned by pd.isn'aBs. In other words, instead of picking out the corresponding values of Ni's by position, it picks out the corresponding values of Ni's by matching index label. After accidentally leaving an ice chest of fish and shrimp in your car for a week while you're on vacation, you're now in the market for a new vehicle. Your insurance didn't cover the loss, so you want to make sure you get a good deal on your new car. Given a series of car asking prices and another series of car fair prices, determine which cars for sale are a good deal. In other words, identify cars whose asking price is less than their fair price. The result should be a list of integer indices corresponding to the good deals and asking prices. Here's the solution I came up with. Let's break it down. Now in practice, I'd probably restructure this data and solve this problem with data frames, but since we haven't learned data frames yet, I've stuck to a series-based solution. So if we do asking prices minus fair prices, it actually uses the index labels to subtract the correct fair prices from each asking price. The problem with this is that the resulting series gets reordered by the index in alphabetical order, so we have to take another approach. My strategy here is basically, for each asking price, get the corresponding fair price. To do that, we can say fairprices.log and feed it the index labels from asking prices. We'll store that result in a variable called allFairPrices. Then we set off-market prices equal to asking prices minus all fair prices. So the good deals are going to be the negative values in this series. Next, we set below fair prices equal to off-market prices less than 0, which gives us a Boolean series indicating whether each car for sale is below its fair price. We'll also chain that with .resetIndex drop equals true to make the index a range index like 0, 1, 2, 3, 4. So now our goal is to pick out the indices corresponding to true values, in this case 0 and 4. If we do below fair prices.log square brackets below fair prices, we'll get back the subseries with just true elements. And then we can chain that with .index.toList to get back the index values in a list. You suspect your local grocery's been price gouging the ground beef. So you and some friends decide to track the price of ground beef every day for 10 days. You've compiled the data into a series called beef prices, whose index represents the day of each recording. Determine which day had the biggest price increase from the prior day. Note that the index of beef prices represents the day tracked, and it's not in order. Here's my solution. Let's break it down. The first thing I do is I use the sort index method to sort the series by its index. I use inPlace equals true to modify the data in place. Now we can interpret the first value of beef prices as the price of beef on the first day, the second value as the price on the second day, and so on. Since we want to get the day with the highest increase in price, we need a way to calculate the difference in price from one day to the next. In other words, we want to build a series where each element represents the change in price from the previous day. So if we had a series to represent the prior day's prices, then we could do beef prices minus prior day prices to get the daily price changes. We can accomplish this with shift. The shift method returns the values of a series offset by some amount. Using periods equals 1 means the ith value in the result will return the I minus 1th value in the original series. In other words, you can imagine the series shifting forward one step, which means we end up with the nan value at the front of the series, and we discard the value at the back of the series. Once we have beef prices and beef prices prev, we can subtract them to get the daily price changes, which we store in a variable called daily changes. Then we can use the series.indexMax method to pick out the index of the largest value in the series. You're organizing a competitive rock skipping league. 6 coaches and 20 players have signed up. Your job is to randomly and fairly determine the teams, assigning players to coaches. Keep in mind that some teams will have 3 players and some teams will have 4 players. Given a series of coaches and a series of players, create a series of random coach to player mappings. The resulting series should have coach names in its index and corresponding player names in its values. Here's the solution I came up with. Let's break it down. The first thing I do is I randomly sort the coaches and players using the .sample method with frac equals 1, which means randomly sample 100% of the series values. By default, this happens without replacement, so what we're doing here is essentially randomly shuffling each series. Next, my goal is to repeat the coaches series like this, until it's at least as long as the players series. Since there's 20 players and 6 coaches, with help from NumPy's seal method, I know I need to repeat coaches 4 times. I can do that by wrapping coaches inside a list and multiplying it by 4, which basically makes a new list with 4 elements, each of which is a reference to the coaches series. Then I can wrap that with pd.concat, which concatenates a sequence of series into a single series. Of course, this new series has 24 elements, which is a little bit longer than our players series, so we'll chain it with .head len players to pick out the first 20 values. Lastly, we'll copy the players series to a variable called result, and then set its index equal to the coach values we generated in the last step. Suppose we've pulled 5 couples on their hobbies. For each couple, determine what hobbies the man has that the woman doesn't have, and what hobbies the woman has that the man doesn't have. Here's my solution. Let's break it down. The key to this solution is to make use of Python's set data structure and its ability to efficiently calculate the difference between two sets. For example, if you have two sets x and y, then x minus y returns a set with the elements in x not in y, and y minus x returns a set with the elements in y not in x. In order to make use of sets for this problem, the first thing we need to do is convert the elements of couples from lists to sets. Apply map works well here as it applies some function to each element of the data frame. In this case, the function is simply set, since set open parens x converts a list x into a set. Now let's compute the hobbies that each woman has that her man doesn't have. We can do that as follows. Let's break it down. Each data frame has a flexible .diff method that calculates the difference between elements. By specifying axis equals 1, we're telling pandas to calculate the difference between elements in each row. And by specifying periods equals 1, we're telling pandas for each element in some row, subtract the element one position behind it. In this case, the result is a data frame where the man column is full of nans and the woman column contains the set difference for woman hobbies minus man hobbies, which tells us what hobbies each woman has that her man doesn't have. The last thing we need to do is just drop the man column. Then we can repeat the same thing for each man. The only difference is that when we call sets.diff, we need to set periods equals -1 to subtract each element one position from the right instead of one position from the left. And then to get our desired output format, we combine the data frames with pd.concat and reuse apply map to convert the sets to lists. Whenever your friends John and Judy visit you together, y'all have a party. Given a data frame with 10 rows representing the next 10 days of your schedule, and whether John and Judy are scheduled to make an appearance, insert a new column called Days Till Party that indicates how many days until the next party relative to each day. Days Till Party should be 0 on days where a party occurs, 1 on days where a party doesn't occur but will occur the next day, and so on. Here's the solution I came up with. Let's break it down. The first step is to build a series that indicates whether each day is a party. Next, I reverse the series and then call CumSum, which calculates the cumulative sum of the values, keeping in mind that true is synonymous with the value 1 and false is synonymous with the value 0. This has the effect of grouping indexes or days together which look forward to the same party. For example, days 1, 2, 3, 4, and 5 all have ID 1 because they're all associated with the same party that occurs on day 5. Next, party.groupBy open parens groups partitions the data in the party series based on unique values in groups and maps them back to the party series based on matching index labels. For example, index labels 9, 8, 7, and 6 are going to get grouped together, index labels 5, 4, 3, 2, and 1 are going to get grouped together, and index label 0 is going to get grouped on its own. Then the CumCount method simply counts the elements in each group, like 0, 1, 2, 3, 0, 1, 2, 3, 4, and so on, except I use ascending equals false to count backwards. And that's going to give us the days until the next party. You can see it if we tack that on to the original data frame. The only issue is that after the last known party, we really should have NAs. So if we pick out the index of the last known party, which we can do with party.loc square brackets party dot index square brackets -1, then we can set everything after that index equal to NA. You own a collection of vending machines and you want to evaluate your inventory. Given a data frame of machine product stock, determine the number of machines carrying each product and how many of them are out of stock. In other words, build a new data frame with product as the row index and calculated columns in machines and in machines empty. Here's the solution I came up with. The first thing I do is build a count0 function that takes a series and counts the number of elements which are 0. Then I group the data frame by product and use .ag with some named tuples to count the number of rows in each group, i.e. the number of machines carrying each product, and to count the number of machines out of stock for each product. Given a data frame of married couples and a separate data frame with each person's age, identify Cradle Robbers, people who are at least 20 years older than their spouse and whose spouse is under the age of 30. Here's the solution I came up with. Let's break it down. The first thing I do is convert ages from a data frame to a series of ages indexed by the name of each person. Then I call ages.loc square brackets couples.person1 to get the age of each person1. I want to insert that as a column in the couples data frame called age1, so I do couples square brackets open quotes age1 equals ages.loc square brackets couples.person1 dot to numpy. Now, if we didn't use dot to numpy, which converts this series into a numpy array, Pandas would try to use index alignment, inserting values from the right-hand side into the left-hand side using matching index labels, which isn't what we want. So then I do essentially the same thing to get the age of each person too. And then I do some basic Boolean filtering to identify cases where person 1 is a cradle robber and cases where person 2 is a cradle robber. Lastly, I use pd.concat to concatenate those series together and identify Adam and Rachel as the cradle robbers. Fed up with your city's roads, you go around collecting data on potholes in your area. Due to an unfortunate coffee spill, you lost bits and pieces of your data. So given your data frame of pothole measurements, discard rows where more than half the values are nan. Otherwise, impute nans with the average value per column, unless the column is non-numeric, in which case use the mode. Here's the solution I came up with. Let's break it down. Data frames have an isNull method that checks if each element is null. In this case, potholes.isNull returns a data frame with the same shape as potholes, full of Boolean values indicating whether each element is null. If we chain that with .sum axis equals 1, we get back the sum of true values, i.e. null values, in each row. If we compare that to half the number of columns in the data frame, it'll tell us which rows we need to drop. But before we drop those rows, we should use the data they have to help us fill in nans in other locations. Now, potholes.mean returns a series with the average value excluding nans in each numeric column, which we can use in conjunction with potholes.fillInA to fill in missing values. Next, we fill in missing values for the location column. potholes.location.mode gives us the mode of location, so we pass that into potholes.location.fillinA with inPlace equals true. The only problem is that potholes.location.mode returns a series, and when you pass a series into fillinA, Pandas uses index alignment to map the fill values into the original series based on matching index labels. To get around this, we chain potholes.location.mode with .i@(0) to pick out the first value in the mode series, which in turn fills all the nans in the location column. Lastly, we get rid of rows we're supposed to exclude via potholes.loc(negation drop rows, because we want to retain rows where the value in drop rows is false. And now we have a nice clean data set we can present to our city council. You have a data frame called schedules that represents the daily schedule of each student in a school. For example, if Ryan attends 4 classes, math, English, history, and chemistry, your schedules data frame will have 4 rows for Ryan in the order he attends each class. You have this idea that the sequence of class-to-class transitions affects students' grades. For instance, you suspect that Ryan would do better in his chemistry class if it immediately followed his math class instead of his history class. Determine the average and median chemistry grade for groups of students based on the class they have immediately prior to chemistry. Also, report how many students fall into each group. Here's the solution I came up with. Let's break it down. The first thing I do is insert a new column into schedules called prev class that tells the previous class for each student. The trick here is to group by student ID and then use transform with the series shift method so that for each student ID, the class series shifts forward 1 period. Then I group by class in prev class and aggregate taking the count of student IDs, average grade, and median grade. And lastly, I use the .xs method with key equals chemistry, axis equals 0, and level equals 1 to pick out class pairs that end with chemistry, and then I chain that with sort values med grade to make the output a little more insightful. You developed a multiplayer indie game called Rose Thorn. Players compete in one of 2 venues, the ocean or the desert. You track the outcome of 5 games between 3 players in a data frame called games, and now you want to analyze the data. Convert the games data frame into a new data frame that identifies how many times each player placement occurs per venue, specifically with venue as the row index and player placed as the column multi-index. Here's the solution I came up with. Let's break it down. The first step is to call games.melt, setting ID vars equals venue, var name equals player, and value name equals placed. Conceptually, you could imagine this as stacking the columns Bella1, Billy Bob, and No Soup for You into a single column. Next, if we group the data by venue player placed, then aggregate the groups with size, we get back the count of rows in each group. This tells us how many times each player got each placement for each venue, amongst the triplets that actually occurred in the data. However, it'd be nice if we also had groups for triplets that didn't occur, like Desert Billy Bob 3rd, or Ocean No Soup for You 2nd. There's a few ways we can fix this, but one really cool way is, let's go back to step 1 and convert venue, player, and place to categoricals. Now when we group the data in step 2, all of those unobserved triplets are actually included in the result. At this point, step 2 is a data frame with a 3-level multi-index. If we reshape it using unstack with level equals the list player placed to move the player and placed levels out of the row index and into the column index, we get back our desired result. Given a series of product descriptions like birch table measures 3 feet by 6 feet by 2 feet, estimate the volume of each product. I came up with 2 solutions to this problem, both of which use regular expressions. Now, even though we didn't cover regular expressions in the course, I included this problem because once you do learn regular expressions, you'll want to know how to use them with pandas, and this will give you a good chance to see how they're useful. So here's the first solution. This bit here is a regular expression, and you can tell because the string has an R right before it. This bit, and this bit are called capture groups because they're enclosed with parentheses. Inside each capture group is a regular expression pattern, and in this case they're all /d plus. In regex, /d means any digit, so it matches any numbers 0 through 9, and plus means one or more matches. So when we do descriptions.str.extract and pass in this regular expression, it looks for one or more digits, followed by '(x), followed by one or more digits, followed by '(x), followed by one or more digits, followed by apostrophe. And what gets returned is a data frame with the values identified by each capture group. Looking at the first string in the descriptions, the regular expression matches this substring, and the capture groups pick up these substrings. Now, str.extract returns strings, so we'll convert those to ints. And then we can do dims.product axis equals 1 to do row products, calculating the volume of each product. So my second solution is nearly the same, except it uses str.extract all with one capture group. Obviously, this returns every matching occurrence of one or more digits followed by an apostrophe, which is a little less bulletproof than the previous solution, but it works for this example. Then I convert dims from strings to ints, just like before. And since the index of dims is a multi-index of input row match number pairs, I want to group the data by input row, so level 0 of the multi-index, and aggregate the groups taking the product of series values. You run an e-commerce site called shoesfordogs.com. You want to do some analysis of your visitors, so you compile a data frame called hits that represents each time a visitor hits some page on your site. You suspect that the undocumented third-party tracking system on your website is buggy and sometimes splits one session into 2 or more session IDs. You want to correct this behavior by creating a field called session group ID that stitches broken session IDs together. 2 sessions A and B should belong to the same session group if 1. They have the same visitor ID, and 2. Their hits overlap in time, or the latest hit from A is within 5 minutes of the earliest hit from B, or vice versa. Also, associativity applies. So if A is grouped with B and B is grouped with C, then A should be grouped with C as well. Create a column in hits called session group ID that identifies when hits belong to the same session group. Here's the solution I came up with. Let's break it down. The first part of my solution is to sort the hits data by visitor ID and date time in that order. This isn't a necessary step, but it makes the data a little easier to digest, and you can actually see where some session breaks occur. For example, for visitor 1, session 102 ended just 4 minutes before 101 began, so we're going to want to stitch those into the same session group. Another example is, for visitor 3, you can see where the session IDs flip between 302, 303, and 300. Ultimately, these should all get stitched into the same session group, because 302 had the earliest and latest hit for this visitor. So the first real part of the solution is to group the data by visitor ID and session ID, and then aggregate the groups taking the min and max of each datetime. I put this in a variable called sessions, and it gives us a look at one row per session as defined by our broken tracking software. Next, I sort the sessions by visitor ID and datetime min in that order. My next step is to add 5 minutes to datetime max, which we can do with sessions.datetime_max plus pd.timeDelta minutes equals 5. This basically tells us, if you look at some session, that if any subsequent session for the same visitor starts on or before this datetime, that they should be grouped together. For example, let's look at session 403. The first one started by visitor 4. The session ended at 12:21 a.m., so any subsequent session for visitor 4 that started on or before 12:26 a.m. should get grouped with session 403. In this case, that means both sessions 400 and 402 should get grouped with 403. In order to create a link between these, we can take a cumulative max of datetime max P5. That ends up looking like this. Now, we still haven't quite linked session 400 and 402. To do that, we need to get the previous datetime max P5 cum max within each visitor ID, which we can do like this. Then we check if each session should be grouped with the one in the previous row by checking if its datetime min is less than or equal to datetime max P5 cum max prev. Now, wherever you see a true value, we want to give that record the same ID as the one before it. And wherever you see a false value, we want to create a new ID. A trick to do this is to negate these Boolean values and then take their cumulative sum. Remember, false is synonymous with 0 and true is synonymous with 1, so it's like taking a cumulative sum of zeros and ones. The last step is just to insert the session group IDs back into the hits table, which we can do with a simple inner join. You own a gym for pregnant women called OBGYM, and you recently opened a second location. You'd like to analyze its performance, but your reporting software has given you the sales data in an awkward format. Reshape it into a data frame like this. I came up with 2 solutions to this problem. Here's my first. In this case, we want to reshape the data from long to wide format. So the first thing we do is pivot the sales data with index equals date and columns equals store ID. Obviously, this creates some columns we don't need, so we can chain that with drop in A axis equals 1, which drops columns with nan values. Right now, we have a multi-index for the columns. We can flatten that index just by setting the columns equal to a list of strings like this. But if we want to make that a little more dynamic, we can use list comprehension combined with an if-else statement and some f strings like this. In English, this says, for x and y in sol1.columns, keep in mind sol1.columns is basically a list of pairs. If the last character in x is either a 1 or a 2, then make a new string by concatenating x minus its last character and y with an underscore. Otherwise, concatenate all of x and y with an underscore. Here's my second solution. Here I set the index of sales as date, store ID pairs. Then I can call unstack, which by default pulls the last level of the row multi-index, in this case store ID, out of the row index and into the column index. From there, we clean it up just as we did in the last solution. You track the whereabouts of 100 individuals in a data frame called whereabouts. Each person has a corresponding list of place IDs indicating the places they visited in the recent week. You also track which places have been exposed to COVID-19 in a list called exposed. For each person, identify the places they visited which have been exposed. Make this a new list column in whereabouts called exposures. I came up with 2 solutions to this problem. Here's my first. Let's break it down. So, one line, pretty good, right? Basically, all this does is it uses apply to apply a function to each value in the places column. The function we apply is one we make up on the fly with lambda. In this case, the input x is a list. If we convert that to a set, and then convert the list of exposed places to a set, we can get the intersection of those 2 sets, i.e. the values in both sets, and then wrap that with list to convert back to a list. Here's my second solution. It's a little bit longer. Now, the strategy here is to expand whereabouts so that we get 1 row per person place pair, then filter the rows where place is one of the exposed places, and then clean up the data from there. So the first step is to expand whereabouts, which we can do using the explode method with column equals places. Next, we set filtered equal to expanded.loc square brackets expanded.places.isIn exposed to select rows where place is one of the exposed places. Then we group the data by person ID, aggregating the exposed places with a list. We'll also rename the places column to exposures. Then we merge back to whereabouts using a left join as a way to insert this column of exposures into the whereabouts data frame. Unfortunately, you can't use fill_in_a to fill nans with an empty list, so to replace these nans with empty lists, we have to do something like this. Here, lambda x returns x if it's already a list, otherwise it returns an empty list. Given a series called Pickle, replace nans using the following algorithm. For each nan, get the nearest non-nan value before and after it, and then replace nan with the minimum of those 2 non-nan values. For nans on or near the endpoints of the series, use the closest non-nan value. Here's the solution I came up with. Let's break it down. Series has a method called ffill, which stands for forward fill, that shifts the series values forward to fill nans. Similarly, there's a method called bfill that stands for backfill, that does the same thing but backwards. So the first step in my solution is to assign the result of ffill to a variable called prevs, and assign the result of bfill to a variable called next. Then, we need to get the minimum of each pair of values from prevs and nexts. If we put the series in a list, we can concatenate them into a 2-column data frame using pd.concat with axis equals 1. Then we can chain that with .min axis equals 1 to get the row-wise mins. Note that nan in the last row is ignored and the min returned is 1.9. Lastly, we can pass the series into pickle.fill_in_a in order to fill missing values with matching index labels. You own a national restaurant chain called Apple Wasps. To increase sales, you decide to launch a multi-regional television marketing campaign. At the end of the campaign, you have a table of commercials indicating when and where each commercial aired, and a table of sales indicating when and where customers generated sales. In order to analyze the performance of each commercial, map each sale to the commercial that aired prior to the sale in the same region. Here's the solution I came up with. Let's break it down. So what we want to do in this case is something called a rolling join. In Pandas, it's implemented with the function merge as of. I'll explain what that is in a second, but first we need to sort commercials and sales by date time. Now visualize the sales data like this, and the commercials data like this. What we want to do is, for each region, roll the sales data backwards to the nearest commercial. This is exactly the functionality provided by merge as of. So in this case, we call pd.merge as of, left equals sales, right equals commercials, on equals date time, by equals region, and direction equals backward. And we get back a table with every sale and the nearest commercial ID on or before the sale date in the same region. Define a person's family IQ score as 0.5 times IQ score plus 0.5 times relatives IQ score, where relatives IQ score is the average IQ score of that person's parents, full siblings, and children. Given a data set of people and their IQ scores, determine who has the highest family IQ score. Here's the solution I came up with. It's kind of long, but I think the code's longer than the actual logic, so let's go ahead and break it down. Here's the strategy. I want to build a data set of moms with ID, mom IQ, a data set of dads like ID, dad IQ, a data set of siblings like ID, sibling IQ, and a data set of children like ID, child IQ. And then I want to concatenate those into one tall data frame of relatives that has every ID, relative IQ. From there, I can calculate the average relative IQs, pipe those back into the person's data frame, and calculate each person's family IQ score. So as a first step, let's build that moms table which has ID, mom IQ, and only rows where mom ID and mom IQ exist. For that, I can do pd.merge, setting left equals person's ID mom ID, right equals person's ID IQ, how equals inner, left on equals mom ID, right on equals ID, and suffixes equals the list, empty quotes, underscore relative. Note that I'm inner joining the person's data frame to itself, but in the left table I join on mom ID, and in the right table I join on ID. Also, the output isn't exactly what we said we wanted, but it has more or less the same meaning. Then we do nearly the same thing to build a table of dads. To get full siblings, we have to join them both mom ID and dad ID. We also have to drop rows where mom ID or dad ID is NA. And we have to exclude matches where ID from the left table matches ID from the right table, because you can't be a sibling of yourself. And then for children, we concatenate the children of fathers and the children of mothers into a single data frame. Notice the column renaming that happens, where dad ID becomes ID, and ID becomes ID underscore relative. Now we can combine all the relatives into a single data frame. And then group the data by ID, measuring the average IQ of each person's relatives. Now we need to get the average relative IQs into the person's data frame, which we can do with some simple index alignment. We'll start by setting the index of persons to be ID, then we just set average rel IQ equal to average relative IQs. And then we can calculate each person's family IQ score. Lastly, we identify the person with the highest family IQ score using index max, and the winner is person 83. Given a data set of concerts, count the number of concerts per artist venue pair per year month. Make the resulting table be a wide table, one row per year month, with a column for each unique artist-venue pair. Use the cross product of the artists and venues series to determine which artist-venue pairs to include in the result. I came up with 2 solutions to this problem, so here's my first solution. So the first thing I do is determine the set of artist-venue pairs to consider. These will be the cross product of values in the artist series with the values in the venue series. One way to get a cross product of 2 series is to use the from product constructor multi-index like this. Now, if I do a left join from concerts onto this multi-index, I'll get back only concerts with the artist-venue pairs I care about, including pairs that don't have any concerts. In order to do that, I need to convert the artist venues multi-index into an empty data frame and set it as the left table. I'll set the row index of concerts as artist venue and make that the right table. I'll join on artist and venue, and I'll specify the join type as left. Now I'll infer year month from date using concerts2.date.dt.2 open parens open quotes capital M for monthly. And then lastly, I'll pivot concerts2 using index equals year month, values equals date, columns equals the list artist venue, agfunc equals count, fill value equals 0, and drop in A equals false. Here's my second solution. The first thing I do is convert the artist and venue fields in concerts to categoricals, whose categories are given by the artists and venues series. Notice that this converted the venue Red Rocks to Nan, because you can't have a categorical with a value that's not in its list of categories. So the second thing I do is drop rows with a Nan value. Then I insert a year month field just like before. And lastly, I use pivot table just like before. In this case, every combination of artist category, venue category is included in the column set, even categories that didn't have observations in concerts too, like the rolling sums.